First I wanted to ask the panel if any of you had any off-the-cuff remarks you wanted to make. No pressure. You don't have to. We have plenty of questions, which will be up soon. I have a couple myself. Those were all very interesting talks. Here we go. But while we're getting warmed up, and they'll be over here, which you also probably can't see. So I will be reading the questions to you. But since I've got the microphone, I'm going to ask. Libby, you pointed out that the ECMWF and presumably the other weather models and such do not have this prediction skill that you can capture using your fairly simple statistical relationship. Is that because the models don't capture this relationship at all, or do they have, have you done any diagnostics on that? You may not have an answer to that. But.
Yeah, no, lots of people have looked into the phenomena, especially the Madden-Julian oscillation in these dynamical models, and it's really hard. Clouds are hard, precipitation is hard, and then you're going to connect the tropics with the high latitudes. To get that wave out of the tropics into mid-latitudes involves what we call the wave guide, which is where the jet stream is. Jim showed that, this is climate models, but our models just have a hard time putting that jet stream in quite the right spot. You put it in slightly the wrong place, you're going to steer your storms into slightly different areas. So once you get out beyond about 2 weeks, all that extra information the models had from giving it today's initial values just really go away, and these biases just become a real problem. So it's possible. I will say, weather models are great, but something that is exciting is that weather models can do an okay job at the Madden-Julian oscillation predictions, say in a week time, and you want to know what are these storms in the tropics going to do in 7 days. Now I'm talking about 3 and 4 weeks, but the models are pretty good at, say, 5 to 7 days. So what we've actually done is said, okay, I'm going to use these dynamical models, our weather models, to predict what the Madden-Julian oscillation is going to do in 7 days. And then from there, I'm going to piggyback off my statistical model. And it actually shows, I was surprised, it just shifts everything and we get an extra week in lead time. So instead of, say, making predictions out 4 weeks, we can now make these skillful predictions out 5 weeks. So I think there is a really neat role to be played between what the weather models really can do and are very good at, and then leveraging some of these relationships inherent in the data itself.
Very cool.
Yeah, I think one thing is, the thing to think about with the MJO is it has this sort of inertia that you can take advantage of. Its lifetime is approximately, its period is about 40 days, but you can use that to your advantage in terms of prediction. And then in regard to the tropical extratropical conundrum or challenge, it's like what Libby was saying, it's hard enough to be able to simulate the Madden-Julian oscillation. It's a multi-scale phenomenon. You're essentially having to simulate individual clouds. The model can't obviously do that, but that's the end goal. But then you also have to represent not only that, and not only the tropical circulation, you also have to represent the extratropical circulation. So it's like anywhere along that line, if you have a failure, the whole thing's going to break down. So that's the essence of the challenge, I think.
Okay. Thank you. By the way, if anybody wants to jump in or stretch your arms because you've been sitting for a long time. We've got one here.
I think for Libby, I too have been thinking about this notion of forecast of opportunity. One thing that worries me with it is the opportunity to miss an extreme event. So we can't forecast it, so we don't forecast it, and it happens. And so this is kind of for Roger too. Do we totally lose people's confidence by completely missing a major event? And so that's one thing I sort of worry about in this, because I do think this forecast of opportunity has a lot of traction, but I'm also worried about if we completely blow an extreme event.
I guess one question for you before I answer your question is, Are you saying we'd be better off not making these at all because of loss of you know?
No, I think no, fair enough. What I'm sort of worried about is how do we communicate
Yeah,
to
okay.
people that there's going to be extreme events that we miss.
From the communication side. Yeah, I get it. Okay, cool. Because I was going to say, to zeroth order right now, we don't really have anything on these time scales. So some information is better, I would think, than nothing. But then Ben's also saying, but the second you start giving people people things, if you don't communicate it right, they're going to lose all confidence because we missed this one big event. Yeah, and I mean, especially the way that I have framed the statistical side of this, not the weather modeling dynamical side, this is inherently going to go towards the mean, or sort of get the average behavior, because it's when we have the average behavior that it does okay. Now, I'm predicting here something absurdly easy, or simple. It's not easy. Take it back. Simple, which is, more rainfall than normal or less rainfall than normal. One could imagine, if we had skill there, changing that to being sort of like what Jim was doing and saying, do we have more than the 95th percentile? Do we have less than the 5th percentile? So actually formulating these in terms of the extremes themselves. The problem with that really is that when you get out to the extremes, there aren't enough of them to learn anything from them. This is not answering your question, I am aware. But more saying that you're absolutely right. This framework I've set up here, as it stands right now, is more of an average behavior rather than the tails. Yeah.
Yeah. So one of the issues we had when in the extended drought in California was, in fact, it was a forecast of opportunity because we didn't have ENSO, we didn't have, but looking in the North Pacific, as everybody knows, and elsewhere, you began to see some signs, right? So that's one, a stop clock is right twice a day, right? So the issue, however, in communicating with Southern California and elsewhere in that, and there's an analog here until we start doing these operationally, was really to be able to show from the median values what could be outside of the different ranges, given different likelihoods, and be very clear with folks that those are also good forecasts. It's not that they're failed, it's not they're busted, they're within the range of things that can happen. And that's been the only way we've gotten with folks moving outside of the crazy, tercile stuff, and I only said that because John's behind you. But the idea is that as long as every time we presented, we were able to say, and here are other things that will happen, but is this usable enough? Now, we have that big issue on the Colorado River right now for long-term projections, which is there's a wide spread, but for most of them, they're negative. And so we focus on whether or not the accuracy of that drop in, let's say, 10% on average means something for planning, without going into what the full spread of potential distributions are, and picking a few of the ones that could seem like a failed forecast and explain to folks that that might happen, and it takes a while to do it. And the only way we do it is to have people who are actually on the job explain it to other people versus having the forecasters explain it. It's the only way we've been able to get around the sort of, what's an acceptable failure.
Yes, I thought you might have something to say.
Yes.
Thanks. I'm John Gotchar from the Client Prediction Center. So, as introduced by Roger earlier, I wanted to kind of touch on a few points, actually. One, first, that Ben made is that, those cases that you mentioned about missing forecasts of opportunity, I can tell you from firsthand experience, do happen, and they happen pretty frequently. One example, I think, unfortunately, was, if folks remember, just a few years ago, the latest in the round of Super El Niños, 2015-16, how the drought in the West, California, was at very severe exceptional levels. Given all the indications we had from all the information tools that we could use, we ended up making a forecast pretty aggressive, 60-70% probability of above normal, let's say tercile for you, Roger. But there was others, actually, other folks saying near 100% chance or 90% chance. And so to get at, I think Ben's point is kind of the piggyback on what you were saying is we made a tremendous effort to try and address that, knowing that if you have a perfect forecast, reliability forecast system, whether it be statistical, dynamical, human, whatever you want to call it, even a 90% probability is expected to be wrong once out of 10 times. And 6 or 7 for 60 or 70% probability. So we've tried to do things like pie charts and stuff that seems to help and show there's different probabilities. And so it's a long-term problem for us over many years or decades. And so we try to approach it that way. I think we made some progress, but it's a real messaging issue, and it's a real challenge, and will be for a long time, because if you recall the next year when we had a La Nina, the West came out of drought, which was typically drier in California.
Yeah. It's a great point. I just wanted to add that from that standpoint, John, the issue of how you create, through the universities and others, the partnership to do that explanation is critical on an ongoing basis. And the idea is not to convince people that the forecast is wrong or right, but that it's a good forecast as could be expected. And the way you do that is by doing what John is saying, that these are also likely. The main thing is for people to believe that the process is sound.
And just one quick follow-up to that is the reason for that, to follow on with what we've made an effort recently, at least at CPC and NOAA in general, of social science efforts to try and better understand how people actually receive the information that as scientists, we in the past many times have just created something and thrown it out there and just use it. Now we're trying to take the other way around. We're trying to have them involved in the process from the start.
Yeah, there's actually a story where decisions were made based on, this is about 18 years ago, before most of you were born probably. But this was about Lake Okeechobee actually, that, for 5 years, lake had been very high. And so really, people who are concerned about the ecology of the lake wanted to draw down the lake. So in about 1999, I think, or 2000, they decided to let 5 feet of water out of the lake. That's a lot of water. And they didn't know, and they used at that time we had the climatology forecast from the CPC, and that was the only thing that was available. But they didn't know they were in the middle of a 1 in 200-year drought at that time. And the public never forgot that incident. And they reminded the agency, I think at the time, for like 5 years that, look what you did, at that time. So these forecasts, even once, could have lasting damage. So that's why I am assuming the communication or the probabilistic forecasts are very important, and to educate them how to interpret those.
Okay. Okay.
So there's been a lot more attention recently, at least conceptually, with the science trying to catch up on compound hazards and cascading risks, complex risks, you name it. I would be really interested to hear from your perspective kind of where that fits into the prediction spectrum, both in terms of time frame, but also complexity. If it's hot and windy, if there's a cyclone and it's hot together, those are very different outcomes, especially for the management relevant timescales as well.
Yeah, I could maybe start. So this is an important planning question because, we have compounding factors. And right now, the communities assume they all occur at the same time, and very conservative designs they come up with. In other words, 100-year rainfall coincides with 100-year sea level. So the way it's being done right now is to use what they call joint probability, and that is a bit more complex because for 2 reasons. One is there's not enough events of extreme events to understand that joint probability. In other words, we don't have simultaneous events. And really, I believe that we have to generate some synthetic data sets on compound events. And then use the joint probability approach, and I mentioned copulas, to develop these conditional probabilities. What is, can we come up with a conditional probability distributions based on those drivers and stresses?
This is showing up as you expect. This is showing up a lot in the copulas, not the movie maker, the joint probability. Yeah, we're seeing hotter droughts, right? And the idea behind hotter droughts is that they actually create greater mortality than almost any other hazard. It's showing up in a lot of the analyses, but from the standpoint of compound hazards, there's also an interest in not just the joint probability of the events, but the joint probability of the interaction of those events with technical hazards. And the classic case of that is during Hurricane Harvey, when the biggest risk was not so much the wind, but during the flooding, having toxic stuff leak into the water. This is why the resilience approach, the networks that cause those things, are critical. But we're seeing much more interest in basically joint events, and even trying to introduce non-climatic events, such as an earthquake happening at the same time or after a hurricane has happened in Haiti. So I think this is getting a lot of interest. I still think it's in the realm of surprises, simply because of what Obi just said. You don't have enough of them. So the case-by-case analysis becomes really important.
I will just add, so from the more just the scientist sort of side of things, I think, as scientists thinking about extremes, this is currently on the forefront, but it's really hard, even with the small amount of data, because, and the hard part is, we actually have to sit down and talk to the experts and these other sub-disciplines. We have to, because it becomes sort of a case-by-case basis. I have collaborations with someone in epidemiology, and when we go through a single event, we have to sit there and talk. She explains to me what the power, what was the grid doing, and I'm telling her where the wind was, and it gets so complicated. And then we have to bring in, okay, what were the sort of the emergency managers doing at the time, and why were they blocked, and it's because something was out. So it becomes so complex that I think we're realizing we have to sit down and have a round table and talk. But it's hard to get all those people together to do that.
But that's exactly the risk to resilience bridge, right? What can be specified from a risk standpoint, even when you do the copulas, together with what is needed from a resilience standpoint. And that's why we develop these regional teams and so on. So it's exactly the point. It's one of the most interesting chapters, as we're waiting for the question, in the Climate Change Science Report is chapter 15. It's probably the most insightful chapter with the least physical science in it, just saying, here's what we don't know about surprises. It's really an insightful admission.
And the two-year follow-up would be then in NCA for volume 2, in terms of saying anything about impacts from those compound events.
Right.
In kind of an endless story and all hypothetical.
Yeah, absolutely.
My name is Peter Penn from CPC. Yeah, my question to Libby. In your machine learning forecast, you mentioned that in the future you may use model data because that's plenty of samples from the model historical runs. But I'm concerning we only have very limited samples from observation. So a model is model. The natural variability, even inside the model, is quite different from observation. So how can we trust the model samples? Or in other words, we still need to do correction for the model data, but with the limited samples from observation, prospectively, what do you think?
Yeah, so that's exactly the issue, is we have all these, we've tens of thousands of years of climate model runs, but we don't want to use them to make a prediction because they put the jet stream in the wrong spot. They don't put the cloud, they can't propagate the MJO. All these reasons we wouldn't want to use it, but the observations are short. Otherwise, if we had a lot of observations, we'd forget the climate models for this problem, and we would just look at observations. And this is at the end, I mentioned the fancy word is transfer learning, but the idea is, I'll use cats and dogs again a little bit, if this helps. And this is from the computer science community. What they say is, we have a lot of one kind of data, but maybe not of another kind. So what we're going to do is we are going to train our machine learning method with images of, I said this example earlier, lions and tigers and bears. And we're going to train it to learn what these different animals are. And what it's going to do, it's going to identify features that make it a lion or a tiger or a bear. Ears. So it identifies, I need to look at ears, I need to look at a nose, I need to look for heads, I need to look for tails. And then we're going to say, okay, we've got a lot of lions and tigers and bears, tens of thousands of images. So it's going to really learn to do well there. But then we only have about, let's see, maybe we only have 2,000 house cats and pet dogs. And that's what we actually want to know. We don't care about lions and tigers and bears. We want to know about pets. Okay, and the neat thing is the network has learned the features that may be relevant, ears, eyes, nose, head, tail, on the data set we have a lot of data from. And then we go and we refine it on the problem we actually care about, which is identifying house pets. And the concept is we don't have a lot of observations, but we're going to use them really intelligently to refine that model. You could sort of think it a little bit like like a Bayesian approach. We start with a prior, and then we're going to update it with our observations. This has worked very, very well in the medical community has this great example where they train on images of objects. So images of this is a spoon, this is a knife, this is a cat, this is a dog. The neural network learns these features, and then it only has a few thousand pictures of malignant tumors or skin cancer on humans. And the neural network has learned features to look for, and then it does a great job on those after it's been refined on the actual problem, which is this tumor cancerous or not? So I think there are links. I can think there's one example in the literature that came out in the last 6 months that shows that this works for ENSO prediction, that actually training on climate models to make seasonal forecasts of ENSO are improved if you train it on thousands of years of climate models, which we know are not perfect at ENSO, and then you refine with the little observations we have. They show that they actually do a better job at predicting ENSO than, well, they argue, than any other model out there. So I'm not saying this is the answer, but it's why I'm excited about the prospect of exploring this further for what it has done in the computer science community.
Sorry, I got a long walk. Interestingly, we've actually touched on a lot of questions that people submitted in the Slido already. But we have a couple of specific ones. Also, if you had a question that you submitted earlier and it didn't get answered and you're angry about that, feel free to stand up and call it out, and we'll see if we can get it answered depending on who's sitting up here. So let's go to this question here for Libby, which is also, I think, extends to most of our other speakers as well. So when applying forecasts of opportunity to the future, can we account for, quantify, or anticipate if skillful regimes may change as the climate changes?
Yeah, this is a great question. So, I mean, I think the answer is in part yes. And the reason is, and I think this is, at least in my view, important for why we need to understand why we have skill, in the present day in the first place. We actually have to understand the processes and mechanisms, so then we can go and look and say climate models and understand how those mechanisms change. I don't think our climate models are good enough to be getting at the scales we're talking about. As Jim said, they do okay, say with an atmospheric river, but especially if you go even smaller scale than that, they're not meant to simulate those tiny scales. So it's really understanding the processes at the large scale and how those may change, I think, that are going to lead to any ability to answer this. And that's one of the reasons I put a lot of emphasis on something like tropical convection and the Madden-Julian oscillation, is because that's a scale and a process that maybe we can start to understand some pieces, at least, of how that will change. And then we can follow the links, if you will, follow the arrows to the future. So at what might happen. As an example, one possible response of the storm tracks over the Pacific Ocean to climate warming is that the storm tracks will shift towards the north. They'll shift towards the Arctic. If that happens, the types of maps that I'm showing you, I would expect to have a shift in where we have skillful forecasts of opportunity, because those are going to go along with where these storms are being sent in the first place. And so in that way, if we understand these large-scale changes due to climate change, we might be able to actually understand how these regions of skillful forecasts of opportunity will also change. So if right now, today, the MJO is really useful for Southern California and predicting precipitation, it's possible it won't be in 20 years or 30 years or 60 years. And then on top of that, I mentioned that how the MJO interacts with mid-latitudes could also change. And so then the question is, is everything we're learning today no longer going to be applicable in the future or not? And I think that's still a very open question.
So switching subjects a little bit, Obey, you're kind of the go-to guy for Florida rainfall. Everybody recognizes that. So what are you advising people on, in terms of these sort of midterm climate change timescales, the next 10, 15, 25 years? What are you advising them in terms of planning? Or what are you advising them on what to use for their planning? How are you informing them, given that from your perspective, the model data, the regional downscaling data is of very limited use? How are you informing them?
Yeah, I think it's similar to the sea level rise projections, right? So, what do you advise people in terms of projections? So I look at it as a risk-based framing problem, right? So if you're designing a small culvert on the road and the failure of which you don't care, you want, and particularly if your design life is only 20 years, you would say use Atlas 14, don't worry about climate change. Now, if you're designing something like a nuclear power plant or major infrastructure that has a 50-year lifespan, now we know that the climate model for rainfalls are very uncertain. I would take, it's a low risk, tolerance problem. And I would recommend them, at 10% based on all the consistent results that we have seen today. It might change in the future, but that's a safe bet on design. So they design for a larger intensity rainfall for the future. They might spend a little bit more money, but it's sort of like a more conservative approach in that sense. That's kind of where things are right now. If I don't have to sign a piece of paper saying no, but I think that's the approach I would take. It all depends on your risk tolerance, design life for the facility that you're advising on, and in that answer could depend, use the existing Atlas 14 data or add 10% to 10 to 15%. That's kind of what I would tell them.
So again, switching gears a little bit, this question has been upvoted a few times and may expand beyond just Roger. But this idea of using different cognitive techniques and so on for communication, I think is probably new to a lot of us scientists who have trouble even just communicating what the heck we're doing, let alone the implications of these things. So I was hoping maybe you could expand a little bit on that. Tell us a little bit more about that. Thanks.
So a lot of the work, and this is people that I work with as opposed to the work I actually do and have written with, has a lot to do with how we think through from one extreme to the next and what happens in terms of people's upfront perception of risk. We have a major project going on in NOAA that I'm involved in called Forecasting a Continuum of Environmental Threats. As you move across the timescales, how do people's perception change as you go from forecast to forecast? In this setting, the reason for pointing out the subseasonal to seasonal sort of intervening frame, just like Libby did on the value, it's a no-brainer to say if you had better information about the future, you'd do something differently, right? So every time we say that, we're actually sort of presuming almost perfect information about the future, unless we do the PDFs right. What we basically are asking folks to do in a series of test cases is ask, Okay, so you have had an event. What can be done in the intervening space between this and the next event on the subseasonal to seasonal timescale? That includes prepositioning. It includes being able to invest in new buildings. There's a window of opportunity that time frame creates if we can say what is likely to happen after a particular event. And that window of opportunity offers the capability to put in new investments for the long term. And that's the way we've been using the windows. Now, what is needed prior to that is all the impacts assessments, all of the sort of network building, the type of thing that Obi does as well, and the liquidity, the funds to act in that space. And that's actually where insurance and other things come in. When I showed the Caribbean Catastrophic Risk Insurance Facility, the role there of that is not to pay back everything you've lost, but to provide enough money for business and countries to restart their basic services so that you can recover quickly. You don't go out and restart it if the likelihood is of another event close to the one that you just had. So as we move through that time frame, we can ask what needs to be emergency, moving people out of the way, and what time do you have to invest for the long term as you move across those. And that's a common sense way of thinking about it. There are the normal sorts of thing that we do on seasonal timescales as well. Is this intervening period wetter or drier than normal? But I'm more interested in what the distribution of events within that window looks like. The reason for that is we might be ready to act and think of a window, but bad ideas have windows too. And people are rapidly moved back into places of risk that might have a flood or some other major event occurring at the same time. So it gives that planning horizon that is not simply all the way out to the season, but it's not just an emergency response that moves people back into places of risk.
Do you have something to say? No.
No, people are running out of gas.
Yeah.
Oh, yeah.
I know.
So there's one cartoon I didn't put up, given the length of the talk, which, Libby's comments inspired me. I have a picture of, and some of you may have seen it, of a cat on a ledge looking at an eagle. And I have the thing that says overconfidence, right? Not in the study. But the cat has analyzed the eagle and goes, I've hired my consultants, I've done my mapping, it has feathers, it has a beak, it's a bird, and I've caught birds before. So it's critical for us to be clear that what we're responding to is not a cognitive map onto something we've responded to before, but use it in the way that she's suggesting, is how do you refine the features? Because we do a lot of that, right? The idea is we think through analogs, and we're using an analog that might not be a perfect map. And that is more deceptive than if it was completely different. If it's completely different, you could say, hey, it's different. I need to do something differently. When it looks like something we've handled before, that's even more deceptive.
So you were talking about how the upfront costs, so the near-term problems are the ones that the general public cares about the most. But we have that desert of predictability on the 2-week to 2-month time scale, and then our predictability skill goes up. And so I'm wondering if the time scale of 2 weeks is closer and more upfront, but we have less skill in prediction, especially of extremes on that time scale. How do you convey that to insurance companies or legislation, people making those decisions for the S2S time scale versus the decadal and longer term time scales?
And others can respond to this. I didn't actually say it's what they care the most about. I'm saying that's if we can't show that our plans can address those as well, then we have a harder time saying, hey, stay outside in the rain, we'll fix this in about 2 months. So one of the things that we're trying to do is this sort of cascading period of risk, right? What can be put into place that might be lost if you do too much prepositioning as well as important? In other words, yes, we get things ahead of droughts in East Africa and things like that elsewhere, but what we want to be able to know is, are there likely to be other events following that? How much do you get ahead of time? So we do that through things like the Famine Early Warning System Network and the World Food Program, in which food and materials are pre-positioned based on what we think the extent of a drought event is, or whatever rain events might be coming in to ameliorate those drought conditions. So there's a planning horizon on which it operates. The question is, and it's up there for the rest of the panel, is what do you do about the white spots? You know, is it a prediction desert, or a place in which we'll have something delicious soon, a prediction dessert? So.
Yeah, I just want to, perhaps it's similar to what I mentioned earlier, this whole idea of dynamic adaptive pathways, so there are two things. One is you want to have near-term benefits of your investment.
Exactly.
So you look near-term, but don't forget about the long-term, because you don't want to preempt yourself, but not having any opportunities in the future to do something different. This is what the dynamic adaptive pathway does. It's like a metro map. You go on one train for a while, when you hit a station like a tipping point, you move to a different pathway. But those pathways needs to be thought out up front for the entire planning horizon. Because like in the case of sea level rise, if a developer comes and builds on that land that you might need later, that means you're preempting yourself, solving the problem later when the things get bad.
Yeah, and the dynamic adaptive approach, the functions have to be integrable. In other words, you can reverse the path, not just go down.
Okay, it's quick. We have another 10 hours to go tomorrow.
Oh, is that?
So.
Yes, well, hello.
I'll just be quick. This is kind of following up on the white space issue, is that I, as much as anyone, know that we want to decrease the white space, but I really feel strongly that indicating white space, whether you label it equal chances or you have a white area in your plot with zero correlation, whatever, it's really important to say that. Okay, if you do not know, it's better to say you do not know, or the uncertainty is so high that you don't want to have somebody make an improper decision. And I'll say people do that all the time. They will, if they don't have information, forecast information or a prediction, as Libby says, a lot of times they'll just go off and make a prediction on their own. And for us to try to communicate, we don't know, if you will, it's an educated I don't know, meaning we have information that tells us the uncertainty, the forecast spread in models or other techniques are very high. I think that's very important and critical that we do that. Of course, we want to shrink those areas, but we really are doing a disservice if we do not communicate that.
It's a really important point. We're seeing it in adaptation. I mean, we put out those maps about where the models agree, and people begin to focus on them as opposed to the blanks, which are blank because the models don't agree. And that doesn't mean nothing's going to happen. But as you know, we can't call ourselves the Equal Chances Prediction Center. Yeah.
On that note, any concluding remarks? I can't wait till tomorrow.
To conclude.
To conclude, yes, exactly.
Actually, I learned a lot today through the talks.
Me too.
Yeah, so
Yeah.
thanks for organizing all those nice talks. So
well.
hopefully tomorrow will be better too.
Yes, we have a lot to look forward
We
to.
have a lot, and just, I'm not talking tomorrow, so I'll say one more thing. What do you get when you cross a mountain climber with a mosquito? You can't. One is a vector and one is a scalar.
Well, on that note, maybe we should have ended with the white space comment.